Good evening, everyone. On behalf of Sri Chandrasekharendra Saraswati Vishwamaha Vidyalaya, it gives me immense pleasure to welcome you all to the Day 4 of AICTE ATAL sponsored 1 week faculty development program on smart energy systems for climate resilient and sustainable development being held today, 25th September of 2025. We are truly honored to have with us distinguished speakers who will be sharing their expertise on the most relevant topics in the field of energy storage technologies and sustainable solutions. For the first session, Dr. Kameswara Satya Prakash Oruganti, title Battery Energy Storage System. And this session 2, we will have Dr. Ramya with the sustainable energy storage through next generation fuel cell technologies. I extend a warm welcome to all the participants, faculty members, and scholars who have joined us for this important session. Your presence enriches the value of this program. Now, to formally introduce our esteemed chief guest of the day, session 1, Dr. Kameshwara Satya Prakash, I request Dr. Anisha to kindly come forward and give the introduction. Thank you.
Anisha madam, you can take over, madam.
Good evening to one and all present here. I'm so happy to introduce Dr. Prakash because he is my batchmate of my purpose graduation. So with that, with over 12 years of professional experience, Dr. Prakash has excelled as a project manager at a leading EPC company, a PhD research scientist, and an assistant professor. Throughout his career, he has developed a profound expertise as a subject matter expert in battery energy storage systems. His extensive hands-on experience in the development of controllers and EV charging stations showcases his technical prowess. Among his significant achievements, he holds a national patent for an advanced charging topology and its associated control mechanism for electric vehicles, highlighting its contribution to innovative technology solutions. His experience extends to designing and sizing PV-powered EV charging stations and BESS for standalone applications, long-duration energy storage and grid-scale applications, specifically addressing the ancillary demands of the grid. Dr. Prakash work during his doctorate has equipped him with a comprehensive understanding of the challenges and requirements unique to long-term energy storage solutions. His hands-on experience in new product development spans from technology readiness level TRL1 to TRL5. Dr. Prakash has successfully transitioned products from concept to fully functional prototypes, ensuring their readiness for commercialization. This skill set enables him to explore and access emerging technologies in power and energy storage for efficiency, reliability, adaptability, and applicability. In his tenure at Fichtner, he has actively contributed to projects involving technical due diligence, design, and development of microgrids based on hybrid power plant systems. These projects have enabled him to leverage his expertise to create sustainable and efficient concept designs and perform high-level system studies via simulation. Welcome you, sir. The screen is yours.
Can you hear me?
Yes, we can hear you, sir.
Okay, thank you, Dr. Anisha, and thank you, Dr. Lakshmi Bhai, and other faculty member. Thank you, Dr. Rajshekar, and all the esteemed faculty. I'm very much proud and feeling good to share a online platform with Dr. Anisha as we travel all the way from our master's degrees. And initially, we were both in power systems studies. We are doing our power systems. However, I transitioned my interest to power electronics and specifically in my PhD. And now even my current portfolio, which I leverage both system studies and then the power electronics controls and the for ancillary services. So yeah, this is a short and brief intro given by Dr. Anisha. Thanks for that. And I hope the participants were a mixed audience where we have professors, faculty members, students as well, and a few members from other universities as well. So I'm just quite open to you all. The presentation going to be like more onto applications, like what we do as Fichtner in across Europe and most of the globe we do, and I particularly take care of Southeast Asia region. So currently I'm situated in Malaysia. So yeah, so with that, I will show you what are the typical applications we are focusing day by day, and then I also give you a possible research avenues. And it is nothing much technical in the presentation, but however, it is going to be the scenarios like where probably you already know, probably some of you already working on it. However, if somebody's need to have some more idea on energy storage, typically on batteries, let me know. And before starting my session, I would like to confer that I am not a chemical engineer, so I don't go into the chemistry of it. So kindly excuse me for that. I am an electrical engineer by profession, so yeah, I will deal only with the electrical part of it. Okay, so I hope with this we can move forward. And if you have any questions, kindly write it in a chat, and then probably Dr. Anisha or Dr. Lakshmi Bhai can convey later, so we can do. No worries in that. Okay, hope let me share my screen first.
Yes, sir. Yes, sir.
Yes. So can you guys see my screen?
Yes,
Hopefully.
it's
Yes,
visible.
yes.
Okay, thank you, Prof. So, so the topic is energy storage technologies. Like as the climate resilience ones, Dr. Anisha was mentioning, I was very much eager to step in. The reason is, I know very well that climate resilience technologies are in need of any part of a country or in the world. So why don't we step in? So that was the initial thought process behind it. And so particularly for this university, the reason is I visit Kanchi actually. So this university is I like the university as well. So in the past, of course, not in the present. So yeah, it is all the motivation to step in. Okay, so I don't go much into the chemistry as I mentioned. So the agenda would be very simple. So first of all, introduction to battery energy storage system, and then followed by why do we need energy storage, and followed by what is best, typically the core components required, and the key application and use cases, and then the research consideration, and then future outlook. So if you see, probably most of our professors who is working in power system and in power electronics, probably by now already they are merged together to come out with various understanding of research, and then they are publishing quality articles, either with your department or with your other faculty members as well. So if you are in that, you will definitely know this. What is it? Actually, it is the front behind the meter and the front the meter, in front of meter and behind the meter scenario, where we will be having. So if you see, this part is in front of the meter where we have a distributed energy resource, what we call DER. So we have a wind, solar, and then pumped hydro. These three are matured technologies, what we have in our country, and of course in all part of the world. And then we have the battery, grid scale battery, or a standalone battery. This is a peak, it's in peak. And some engineers and some experts argue this is a waste of money and then etc. It's going to be occupy the space. That's a different debate, and it's not for now. But however, this is also takes place. It also got quite a interest and investment among huge players in the world. And of course, the thermal generation is the one which we tend to have to cover the base loads. So these are all the technologies everybody knows very well. And this we call it as, like in the front metering or the front metering side. And whereas behind the meter, we have our home buildings. So I think Prof. Sarthi was mentioning about the green buildings, and then even the possible section. The first session I saw, I was there for quite a few minutes. Then he also mentioning green buildings. So yeah, those things, rooftop PVs or come into this category, and then battery energy storage again, where this will be in commercial and industrial, like C&I. In front of the meter, we call industrial or a grid scale level or industry level. This one is a commercial and industrial, C&I we call. And then we also have a EV. As you know very well, in India, we have FAME 1, FAME 2 schemes to promote EVs. And then, of course, we have hydrogen. I don't know how many of them are working in this group on hydrogen, probably hydrogen for transportation or hydrogen for electricity. I don't know, but it is a quite amusing area to work on. And it don't require different specialization. Hopefully, electrical engineers can easily work on that in in the electrolyzer section. So even in India, particularly in our Tamil Nadu in Thoothukudi, we are building one. We in the sense India, not me, not our company. India is building one hydrogen power plant to extract hydrogen from the water to convert into the liquid ammonia and transfer or export to Japan. So this was the recent project was signed by India in Thoothukudi in Tamil Nadu, and the project is carried out by Sembcorp in Singapore. Meaning to say that why we are telling that is there is a huge potential in this domain where the skilled labor is not there. So skilled labor in the sense it's not technicians, it's engineers. So we ourselves call sometimes labor. So skilled labor is very short in conversion of hydrogen to liquid ammonia and vice versa to the electricity. Okay, so this is the behind the meter. So here, if you see that intermittency and timing is the huge opportunity for us as a researcher, as a student, as a future engineer, such as the intermittency is totally depends on the nature. So we don't have a control on this parameter. However, we can tame it, we can adapt it, we can try to beat the intermittency by using storage. So intermittency, I mean to say, is clouds, rain, or any other typical natural calamities, or any other disturbance in a production can be call it as name it as an intermittency, where we can try to overcome that natural intermittency by using the energy storage. But since I'm an electrical engineer, I'm more drifted towards the battery, and there are certain amount of storages are there, certain number of storages are there, different technology. However, I'm not going to bring those into this today's session. Okay. Okay, let's go to the next one. So everybody knows very well why we know the energy storage is basically the duck curve. And probably few professors claim that no, the duck curves became a valley. What I mean by valley is, for example, now the duck curve is like this, right? So meaning to say that from morning 9 a.m. we'll be having the morning and midday dip, and whereas afternoon we'll be having a flat belly, such as there is no active load except the industries or the institutions, and however evening there will be again ramp. But if you look at that, this was quite acceptable in most of the scenario, but however in some part of the world now this duck becomes a valley such as like this, whereas the peak load in the morning and the night, because of thanks to the ChatGPT and other AI technologies, when they are started to step in, we need demand. Everybody is running behind that. However, to power those, we need energy. So it is a challenging for industrial engineers like us and electrical engineers, of course, like us, to understand how to dispatch uninterrupted power supply for the data centers is a huge challenges for us. So now this became a valley from the more of a duck curve. So based on this, how we are going to meet this, or we are going to flatten the curve is something is, so during morning time probably we'll be having a ramping up of solar generation slowly. Okay, and then afternoon it will be peak, and then it again comes down, and then it goes down. So everybody knows, right? Everybody is very good with renewable energy sources. Everybody knows this. There is nothing new here. So however, so at this moment, the solar is more, and then the load demand is less. And however, this load is totally inversely proportional. And sometimes if you take a wind technology, probably if it is located nearby the seashore, like Mahabalipuram, Kanchipuram for us, nighttime will be the peak, and then daytime will be the less, and then again nighttime will be the peak. So this is solar, and this is wind. Okay. So here, the intermittent nature of these two sources, we cannot club into one. And everybody know, even whoever doing the research in the power system stability, they know very well the stability criterion doesn't meet. So we need to worry much to make the system to be stable. So at this moment, we are bringing our best. So what we are going to do is we are going to charge, like, okay, this ramp up period, whatever is the ramp up period is there. Okay, we are going to utilize this region to charge my battery at as fast as possible. Okay, and then I'm also going to discharge my probably say this is the load. Assume the load curve is something like this, and whatever the peak here, this is a curtailed solar PV. So the curtailment is because of either two reasons. One is there is no load to absorb, one thing. Second thing is the injection of solar into the transmission grid is limited. So because of these two, even though we have a generation, we generally tend to avoid, we won't capture that. So we utilize this to also charge the battery, and of course, this region also we try to charge our battery. So it's not something new, anybody can do this, but however the challenging part is how. Okay, so that's what the experts in the field like me and then my company do. And don't worry, I don't present any company slides to you guys, so it will be purely educational purpose. Okay, so just I just want to give you a type of batteries or battery energy storage which we are using in our day-to-day life. A small glimpse. One is, as everybody knows that we have lithium ion. Everybody knows that, popular, and we have a lithium ion polymer. In short, we call LFP. And then we have a vanadium redox flow battery. In short, we call flow batteries. And then now we have a sodium ion battery. So the other batteries, okay, it's there in the categories. I'm not interested in that. The reason is I'm not going to use those in my C&I or industrial and grid scale level. So I'm not interested in that. So these are the four I'm going to concentrate. And here, if you look at the advantages, as you know, the energy efficiency is greater than 90% for lithium ion. And of course, it is more or less 90% and above for all four. There is no doubt in that. And if you see the energy density is available as the footprint of the battery increases. For example, just take an example, your mobile phone consists of 5000 mAh battery. What is the meaning of that? It is 5 ampere hour it can deliver, right? So 5000 milliampere hour means 5 ampere hour. So at 1 hour it will able to deliver 5 amps. So that's the meaning of your mobile phone battery. Just imagine the size of the battery would be this small, right? A sleek pouch cell. So just imagine a prismatic cell with a foot long with 3-inch thickness, where it gives you 320 ampere hour, right? It's a huge. Just compared with 320 ampere hour to 5 ampere hour, just 5, 6 or 30, so 6.4 times bigger. Okay, that's what we are talking here. So like that, the CATL, Panasonic, Samsung, they are manufacturing the cells. So those cells were every day they are coming up with a very much higher footprints with less thermal issues and cathode issues, manufacturing issues. So it's always peak. The efficiency is always at peak. So this is the technology is quite mature. So that's why we prefer lithium ion and lithium ion polymer like LFP. Okay, so and then we have the redox flow batteries. This is quite different. It's basically a flow battery, unlike lithium ion or a sodium ion. This is consists of a tank, a reservoir, not reservoir, sorry, storage tanks where we storage, the cations material and then the anion materials, and we will allow it to flow. So this is a flow battery, and the footprint is typically bigger when compared to the lithium ion polymers like LFPs. LFPs can come in, like for example, 5 megawatt hour battery can come in 20-foot container. Probably this one, the same 5 megawatt hour, if I want to have vanadium redox flow batteries, I need at least 2 40-foot containers. So that's the footprint of the battery. However, the challenging part is that the number of cycles the battery undergoes will be more compared to LFP, such as you don't want to replace it for a huge period like 10 years, long period like 10 years, 15 years without going for augmentation. No. So in lithium ion, generally there might be a need for augmentation in the year 7, and whereas probably we can augment in sizing and then we can go up to 20 years. So vanadium is something which is preferred for the long duration energy storage. However, there is still debates are there among the industrial players who wants to prefer what, and depends on the application they want to prefer. So yes, so within this 4 chemistry, I'm introducing about the typical batteries which we are using in our day-to-day life. However, the other chemistries like aluminum air or some other potassium, okay, those are there. I don't say no, but everything is under probably TRL 2 or 3, such as in the laboratory proof of concept only, nothing much more. So we will go to the next one. Okay, so here, when you talk about a BESS architecture, I need to understand like what is the components needed to, we say BESS. Okay, everybody will have an idea, definitely. I don't deny that. Okay, you put a battery pack, say now you have your laptop have a battery pack, mobile have a battery pack. So e-scooters, probably some of our audience might use already an e-scooter. So okay, you may think, okay, this guy's telling the same thing what I know, of course. But the thing is that the architecture is not simple and similar to whatever we use in our day-to-day life. So EV, the electric vehicles, the architecture is totally different. The powertrain is totally different. Whereas the grid scale energy storage or a standalone energy storage, the architecture is quite different. You can see for example, the cell module pack and then the BMS, up to this, it will be same. I don't deny. But however, after this, the scenario changes. So here, for most of the devices or most of the bikes, what you are using even in e-bikes, the thermal runaway and then the thermal HVAC systems are not that efficient or maybe not present. So there is a possibility of getting caught in fire, explosion, etc. But however, we cannot afford to lose a 5 megawatt hour 20-foot container to undergo into flames. So I need to have a proper HVAC and fire control system. So this is totally a different control system working parallelly with my main system. So there is no compromise in that. And as you know, as most of you know, BMS is nothing but battery management system. So where it will take role of active balancing and then passive balancing of cells during charging and discharging. And of course, we have the HMI, human machine interface. As everybody knows, you want to have a control like your touchscreen tablets. So it will be have a IP65 tablets on the site where we can touch and we can control like what is the setting, how you want to log it, and then you want to do any emergency services, something like that, you can use this. And along with that, we will be having a switch. It's actually a network switch, IP switch, of course. You'll be having a gateway, and then we will be having a multi-pack sensors in terms of, for example, 20 numbers with probably like all the environmental sensors will be in the container, and probably single module may have a single temperature sensor. So n number of sensors we need to bring all the data at one point, and we need to coordinate accordingly based on the flags of sensor data. We need to assign our control parameters so that it will operate in a perfect harmony. So this is up to a battery, the container. But beyond this, we have the master controller or the EMS, energy management system, where we will be using that to communicate with the grid, or if it is an off-grid system, communicate with the local controller. And then, of course, we have a fleet control, ISO, utility, and then we have IEC norms, DERMS, DER, distributed energy resource management systems. Everything comes into picture. So here, this is the primary side, okay? And after this, okay, forgot about the instrumentation part. The power part is okay. I have a battery now, so I need a charger, right? So I need a charger, and at this moment, it's similar to our laptops, like, or EV cars or bikes, where we charge in the same port, we discharge in the same port. And so for that, we have the PCS, where power conversion system we call. It's nothing but a bidirectional DC to DC converter inverter, or DC to AC converter inverter. The DC system is nothing but I'll be having a bidirectional DC-DC converter, where it might be a chopper, or it might be a dual active bridge, or any other like multi-stage dual active bridge, anything, DABs, anything for a DC systems. But if it is an AC system, then I need to go for DC and AC inverters, probably in research. Currently, the one is neutral point clamp inverters. Those inverters are quite good, three-phase inverters, of course. So at one end it would be a DC, and another end it would be a AC, but all bidirectional. And then after that, we'll be having the station transformer, just like any other power plant. And if you take a typical power plant, we will be generating at 110 voltage level, and then we will step up into 110 kV, and then we'll be having a generation station transformer. It's a generation substation, where from there we'll be having multiple feeders. So this is a typical power plant for you. But whereas here we have a station transformer, its only purpose is stepping up and acting as a isolation. Okay, so after that it'd be a grid. So this is a typical BESS architecture. There is nothing new or nothing complex here when compared to a traditional power system. Okay, so as I already mentioned, these are the systems, and apart from these four, the 5, 6, 7 plays a vital role. So as engineers, as academicians, as researchers, we know only these four. Okay, we never worry about 5, 6, 7, because okay, you do a project, you have a prototype, you just build it, and then you test it. That's all. You got a result, publish a paper, move on. But here we need to go 3 more steps than the academic. Here, what we do is thermal management system, environmental control, where we make sure the investment does not go into waste. So I need to protect the investors' money. So as a design engineer, as a consultant, what I do specifically is I make sure this environmental control is as per the IEC standard, or NFPA, the American standard, or ISO standard, or IEEE standard. I need to adhere with this. If this is not there in place, generally we won't allow the system to get certification. So we need to undergo this as crucial. And then 6th one is safety systems, such as on-site safety, like HVAC, and then HVAC. It also, of course, that air conditioning, ventilation, heat, ventilation, and air conditioning. And then we will be also taking care of suppression, fire suppression. Okay, so if there is a thermal runaway, it should not propagate to another cell or another module before 5 minutes. So this is IEC standards we are speaking here. So I need to design my system in a way that it is not propagating. So the battery manufacturer, the BESS manufacturers will follow that. But as a consultant, I need to make sure that they are adhering with the standard. So during my factory assessment test, we will take care of the testing protocol, and we will see that everything is under control. So if some safety parameter is missing, then we will reject the total batch actually. So, and then the auxiliary systems, which is helping your BESS to operate efficiently. Okay, so this 567 is where I will be working much, because as a consultants, we will be mostly work on 567, as we are not R&D, we are not manufacturers, so we won't worry about 124, because the 124 will be taken care by the manufacturers like CATL, Panasonic, Samsung, Lithium, and if you say who else, ABB, Sungrow. So these people will take care of 124 and we will take care of 567. Okay. And okay, coming back to the communications. So in previous slide, we saw the basic components of a BESS. However, how it is communicating. The communication is quite crucial in battery energy storage systems, such as we can give a command to charge, it will charge. As a command to just discharge, it will discharge. But however, it is not as simple as we think. So, you know, up to this, everybody knows. This is a pre-charging resistor, and then we have the BESS batteries in series or parallel in combinations. We have the BMS. So the ECS we will be taking care here. Okay, and we'll be having a main isolator or a switch with to connect and disconnect, and then here we'll be having the PCS, either DC system means DC-DC or DC-AC bidirectional, and then we have a grid. So here, this fire suppression system will work in parallel, but all are connected with either fiber optic cables. So here the challenging thing is how it is communicating. So as a system level, batteries will communicate with the BMS, and then BMS will communicate with the network switch and then to the EMS. Because as a grid, now consider I am the grid, I want to use the BESS for certain application, I need to respect the limitation of the battery pack, such as what is the SOC, the state of charge, what is the SOH, state of health, what is the DOD, depth of discharge of a system. So unlike you know, everybody in day-to-day life we do, even though your phone comes to 15%, you know that you need to connect it. However, you will use it till 10%, 4%, and then you will put in a charger. Everybody do, right? So sometimes that will spoil your battery in a longer run. However, we don't allow that to happen in a grid scale storage system. So we will need to respect the boundary condition of a battery where it gives us indications through the communications. Okay, and whereas if there is some fault in the system, if it is electrical fault, no problem, we will isolate using the isolators. However, if it is within the modules, now the modern systems are there, such as we can isolate even an individual module and we can replace it. It's there. However, if there is a thermal runaway or a thermal propagation, then those signals will be given to the fire suppression system, which will work in parallel and autonomous to the main controller, such as irrespective of all these, if there is a thermal runaway is indicated either by gas or either by temperature, excess temperature, then this system will function. And once the system will function, it will give a command to isolate the BESS system from the grid. So this is how high level communication takes place. So if you look at the Purdue diagram, such as the Purdue is in industrial aspect, we call Purdue because it is a architecture between the operating technology underneath and then the communication layer. So if I'm not wrong, probably everybody know, in communication we studied 7 layers OSI communication, 7 layers of communication, etc. Similar to that. But however, the Purdue is the operating or the operational technology which is underlying. There's a tier 0 where the physical aspect of a system which functions, and then we'll have a multiple tiers of a communication layers. So here in this tier 0, for example, if you see the tier 0, we have, as I mentioned, all this will be work in the previous slide. This will be in the tier 0. However, in the tier 1, we have the field control system, which is a non-IP, such as our master slave BMS will be communicating to it. And then Again, field control system, which is an IP control. It's a tier 2 where our PCS comes into picture because the PCS need to communicate. So say for example, the battery is from CATL or a Samsung. However, your inverter is from ABB. They both need to communicate each other to have a perfect harmony, either using the Goose or either using the power over Ethernet PoE or even PLC, these communications channels, right? So all the systems need to be function properly so that they can create a handshake and then they can function in harmony. So this is a IP based communication in tier 2. Whereas platform information technology, we call a PIT. In tier 3, it comes our EMS and then DERMS. So EMS is within the plant. It might be hybrid like solar with battery or wind with battery or hydro with battery or any of combination of these plus diesel. It's any hybrid. So there might be one power plant controller or we call EMS probably or PPC. So both of these things can be work to make it in harmony with our bus system so that it will be utilized properly. And whereas the DERMS comes from the distribution system operator like DSO. Like in our, I think in Tamil Nadu we have Tangenco, right? Genco, Disco, yeah, I think generation, transmission, distribution, these 3 parameters. And we have the load dispatch center in Mount Road, I think, yeah. So what they do is they do the unit commitment and all your economic dispatch, they do that, right? So the distribution system operator comes into the picture of DERMS, okay, distributed energy resource management system. And whereas in tier 4, we'll be having the servers, fleet control. It might be a third-party system, or it might be the independent power producer, or it might be the one who put money. They'll have the major system. So this is where the more field, this still up to tier 4 and the tier 5, sorry, tier 4, it will be in site only. Okay, it is in the project site. But however, the tier 5, external communication and the PIT management, where this comes to the cybersecurity part. Okay, so here in this Purdue diagram, as the researchers, we will be looking at the aspect of up to tier 2. And as a power system or power electronics, power system guys can come into tier 3, where the power electronics guys will stop in tier 1 and tier 2. However, the computer guys come in the region of tier 5, where the cybersecurity comes into the picture. Okay, so this is a typical Purdue diagram of a BESS architecture. Let's go to the next slide. Okay, now that's up to the architecture and communication, what is happening. Hope you have some, probably you already know, but however you refresh your ideas or probably you heard now, it would be good. Now let's come to the application and use cases. So here we are broadly categorizing into 4. One is grid, power production, C&I, commercial or industrial, and then residential or community. This is behind the meter. Okay. So for grid, we will be typically looking at 2. One is grid resilience, under which we will be having the backup power or a black start, and then power islanding. So there might be professors who already worked in microgrids and probably they worked on island detection techniques, such as if a system, DC system is undergone a fault, or if the grid undergone a fault, then the system need to get islanded. So in order to understand whether the system is islanded or not, we need to monitor island monitoring and island detection. So this is a control problem. Most researchers were working in the period of 2018 to 2021. After that, people stop that and then they move on to microgrids and further into nanogrids. It's okay, it's up to them. So here, black start everybody knows, brown start you know, black start you know. So we will be using a battery for that application when we are talking in terms of grid. And of course, when the grid and the power production, we are talking about energy arbitrage. So here arbitrage is something you need to understand is just like our commodity. You know, whenever the electricity price is high, I want to sell it. Whenever the electricity price is low, I want to buy it. So it goes vice versa. So I am a IPP, independent power producer. I have a battery energy storage system. of say 100 megawatt with 400 megawatt hour. So whenever the current is low, I mean the current electricity charges are less or the low, I want to charge as much as possible. When the charges are more, I want to sell for the profit. So this is an arbitrage. And this arbitrage can be taken place on 3 levels. One is wholesale, and second one is intraday, and third one is reserves. So wholesale means just like our traditional day-to-day concept, entire day I will sell the power and I will buy the power. Okay. And then intraday means whenever there is a demand, I will sell. Whenever there is no demand, I will buy. And then the reserves is something where it is like a premium product, because my battery services will be functioning for a certain period of time only, so that I can sell that for as high as possible. That is like a e-hailing in cabs, something like that. When there is a rain, when there is a peak, the charges will go more, something like that. So yeah, these 3 are the energy arbitrage: on day, ahead, and intraday markets. And of course, frequency regulations, which typically falls under the ancillary services, such as if there is a grid and the load is connected, and if the loads are getting more and there is no flexibility in the grid, what will you do? Generally, this is it comes under load management. We will try to shut down the non-priority load, and then we will, such as the power shutdown, 2 days in the city, 2 hours in the city, 4 hours in the suburb area, something like that. So yeah, so load shutdown we will do. However, if there is a grid which is kind of flexible, even the load shutdown, if you are work in power system, and if you know a little bit of the frequency concept behind it, we don't immediately shut down the loads. We will allow the frequency to get under strain, such as if it is a normal operating frequency is 50 hertz, and if the loads are increasing, my frequency will come down. So my under frequency relay will somewhere operate at 49.5, say. Okay, I don't want to use that, because if it is, then there would be a series of trip connections happening. I don't want to do that. So it's 49.5. So now I have a margin of 0.5 hertz. So in the 0.5 hertz, I will utilize the 0.3 hertz as my strain. So until then, I don't shut down. I will allow my grid to strain as much as possible up to the 0.3 hertz. If it goes further more, then I will shut down the load. As a load dispatch center, this is what people do. So here in the ancillary services, in the frequency response, if the loads are more, we will generally shut down, right? But here, with the help of a bus, what we will do is we will inject the power into the grid. So we will take the load, okay, so that we will make the frequency to 50. We'll make the frequency to ramp up to 50. Okay, now suddenly there is a load rejection. There is no load, and my synchronous generators are running at high speed now. It is now 50.1. So probably you'll have 50.5 as an over frequency relay. I don't want to operate that, so that I need to shut down the unit. So 50.1, by the time I will absorb the power from the grid. So initially I will inject, now I will absorb. So this flexibility I will bring with the help of a bus into the grid. Okay, so of course the T&D support, the existing infrastructure, if it is not supporting, we can use that for charge the battery at one location, you transport it to other. But this part is somewhat, we are not practicing in industry till, because it is not meaningful, but it is a theoretical concept we can still pursue. And then renewable integration, as we earlier discussed, we can integrate our solar, wind, hydro, anything into a picture with a BESS. And what we call, like in commercial, industrial, or the residential, we call selco, such as self-consumption. So whatever we want, we generate ourselves, we consume ourselves. So we don't be a burden to the grid. That's a concept. This here, it might be a grid connected or a standalone systems may play into a picture, or microgrid, nanogrid, you name it. No worries in this. And we have the energy collectives, such as it's a power island. So we will generate in one place, we will store it in another place. It's a power island. In India, it is not at practicing, but in Malaysia, it's already in practice. The power islands, mainly for the data center. Such as very simple, you take some island, uninhabited island, You just make that island into a solar power plant or a wind power plant with a battery. That's all. That's a power island. There is no human being roaming over there. Only the operators. So this is a power island. And we have a power peak load shaving and bill management. You know peak load shaving, right? So we will be managing the loads, and to avoid curtailment, we use that scenario. So this is a typical application and use case with respect to my competitors WSP. Of course, it is more or less same. So here, if I look into specifics of duration of service, how long these ancillary services can be catered. So I have an arbitrage, as I mentioned, firm capacity, and then the operation reserve. So here, firm capacity means I want to beat the intermittent and I want to feed you a constant power without any uninterrupted. You know, the voltage, the power profile should be good. So I will maintain that. And then frequency response, regulation, spinning, and then the load following, and then the black start. So typically, only the frequency response will be in terms of seconds, minutes, nothing more. But the the consistency of will be increased to 1 to 2 hours. But however, the precision from the DERMS or EMS will take and then ramp up your best in terms of seconds. Okay, this is the standards as per our IEC, and IEEE we follow. Such as your system generally, if you take a spinning reserve, like generally hydroelectric power plants called as spinning reserve, because you just open a valve, then there is a production, immediate production. So that's why we call it as a spinning. But however, this is a stationary reserve. So rather than turning the valve, even hydroelectric, the ramp up time will be in terms of minutes, but this will be in the ramp up time would be in seconds. Okay, and this particular use case for the US alone. But however, next slides I will show you Germany, where my company, where my headquarters, and where we are established, and then I also the other global markets. So this is a typical visual explanation for you guys. This is from the ABB. Peak shaving, how it look like. So we will absorb, we will supply, absorb, supply. So whenever there is an excess, we will absorb. Whenever there is a limited, then we will supply. So this is, so during charging time, it's absorb, discharge is supply. So this is our SOC curve, and this is our load curve. Okay, load supply curve. And this is a frequency where 49.98 is a lower threshold and 50.02 is the upper threshold. So this absorb is nothing but charge, such as when there is a load rejection, okay, I'm going to charge, I'm going to absorb. This is going to be the injection where my base is going to discharge. And then this is a firm power. So firm power is something, sometime like I want to give you a constant profile to beat the intermittency. For example, take a solar. If there is a cloud, very simple, if there is a cloud on a, say take an example, 1.2 hectare, sorry, 1.2 acres of plot where I can have 1.1 megawatt approximately, and there is a cloud cover, at least 25% of solar plant will get shaded. And of course, our professors already worked and still working on bypassing the shadow, developing MPPT techniques to overcome the shading effect. Very good. But however, as a best, what we do is we will, when there is an intermittent nature, we will absorb, we will inject. So if there is a more intermittency, we will inject more. When there is a sudden isolation or insulation is more, we will absorb. Something like that. It is in terms of it will range in terms of seconds to minutes, where the charging and discharging will be taking place to provide you the firm power. And coming back to a spinning reserve, just like our hydro, we will be fully charged at any time. And this application, when there is a load demand, then we will quickly discharge. So this is the 4 major cases you can conclude of ancillary services. And beyond this, of course, for example, BESS as a buffer for EV charging, which is my PhD work. I am using the BESS as a buffer, such as for fast charging stations, the grid may not support fast charging. So already our people are working like, okay, fast charging grid cannot work. Okay, let me bring solar, let me bring wind. No, let me go fast charging, like let me develop 300 kilowatt charger. Okay, but still my BESS act as a buffer, such as irrespective of the source, whether it is low, small, big, or whatever it may be, I will use the BESS as a buffer, which is simply as a stabilizer, so that my fast charging will take place, such as I am using a BESS to charge another BESS. So this is my PhD work. If you are interested, we can discuss later on that. And this particular concept, luckily, I am implementing, like I am acting as a lead engineer to deploy in Saudi in one of long duration energy storage pilot study, where the one main BESS or the main storage container will be made up of sodium ion battery, and then the load is nothing but the LFP, lithium ion phosphate. So we will charge the sodium ion from solar, we will use it as a buffer. Whenever this is nothing but this lithium ion phosphate is using as a for the frequency response reserve. So it's very small in size. But however, to charge this, I will be using the sodium ion. So this is the same concept which I did my PhD, and now I'm doing there for the Saudi clients. So it's an interesting one, you know. So that's another application, but it's a direct application, active power application. But whereas these are the ancillary services. Okay, I think now time is 7. Let me quickly go. Okay, so currently in Germany, why specific Germany? Because my company headquarters is in Germany, so we do case studies from there. So currently we have the market like this: energy market, balancing market, and security measures. So this market, like, okay, if you see, okay, where this comes in India, particularly our load dispenser center, we have some 4 to 5 load dispenser center in the entire India. They will play these roles actually, not the Genco, not the transmission guys, but the LDOs will play this. Okay, such as the power exchange is futures and options we don't have in India, but whereas in Europe Union we have most, such as you can trade on energy, just like you are buying shares, you are selling shares, and you are doing some crypto. Similar to that, you can do the energy trading. So this is energy trading, and this is, as I mentioned earlier, wholesale, day ahead. Day ahead is 1 day, day ahead is a forecasting, and then intraday continuous, and then intraday auction. So auction would be like morning at particular time of window, we will bid. Okay, I have this much reserve, I'm ready to inject or ready to provide you this much of megawatt hours at this price. Say for example, 100 euro per megawatt hour, something like that. Okay, this is auction. So whoever gives less price, the operator will take that. So this is auction. And we have a spot contracts and then derivative contracts. So over the counter, such as just like over the counter, like in medicines, we go into a pharmacy and we take that, right? Something like that. We will operate with a DS operator, because unlike India, Germany itself got 700 distribution system operator, more than 700. So it's quite a headache there. So it's like a market, like everybody can buy power and everybody can sell. So like that, we have 700 plus. So this spot contract is something, sometimes it's more beneficial for the independent power producers. But in India, no, this won't come soon, I hope. Because whatever the power is there, we need our power supply for our home itself. Forgot about EVs, right? So whatever we generate, we will give to the grid, either northern grid or southern grid will give. Whereas this already we discussed, and then here we will be like redispatch, renewable curtailment, load shedding. This also we discussed. So these are the typical electricity market in Germany. So here, what would I like to say is, if you are a researcher focusing on energy economics or energy market, so you can create your hypothesis based on these. If you're really into policy with energy trading, etc., because it's not something new, but it is something new to regional, right? Unlike governments or unlike other countries, it is quite challenging for India to adapt, or any other developing nation to adapt. The reason is we are centralized. even though we have a state electricity board in all the state, but all the states we will be giving to the northern grid or southern grid. It's a unified approach, right? So like private players, for example, some states have a private players like Adani, Reliance, they have their own, in Bombay, they have their own electricity network, gas network. Sometimes in future, if it comes, this would be a possible interest if you are keen towards the energy market, energy economics. Okay. And then if you look into the technicals, like how many megawatt hour the batteries involve. Okay, this is some area in Germany, some project in Germany where our company handled. And say, for example, in frequency control response, voltage support, black start and islanding, it's a 10 megawatt and 15 megawatt hour. And of course, we saved 12,000 tons of CO2 equivalent per year. Okay, so this is a 10 million euro is an investment and 1 million annual turnover. So if you look at this number, I can get my 10 million in 10 years, but the battery, the plant will be operating for 20 years. You know, it's a typical payback would be just like even less than PV, we will get the payback here. And I don't think whether audience will be interested in this detail. However, I would like to highlight, I don't want to highlight the number, like the amount, but I would like to highlight the size of the project. So for bulk energy services, like time shifting arbitrage and then wind curtailment, we were deployed 48 megawatt and 50 megawatt hour BESS systems with lithium-ion battery models, and it's owned by Mitsubishi. And for frequency control regulation and balance of volatile PV generation, this is again a firming of power. We were deployed 2 megawatt and 2 megawatt hour capacity. And we also have for ancillary and grid stabilization, we use 50 megawatt and 53. So here the grid stabilization is a term which I would like to emphasize. It is nothing but usage of IBR. Probably your researchers will, or as you are browsing, you know, if you are in power electronics, inverter-based resources, IBR. So if the more and more inverter-based resources are coming into picture, the inertia will be reduced. We need to produce a synthetic inertia. I want to stabilize the grid. So for that, we will use the BESS. You know, you can browse papers if you are interested into it. IBR, inverter-based resources into the grid. You know, IBR-based resources. And then we have again this one is ancillary service. Okay, the same. Here I would like to highlight this one, M5 BAT ACAN. This is battery life optimization for control reserve trading arbitrage. So this particular project is it's not for commercial. It is only a controlled reserve. So it's purely energy trading. Okay, so here they use multiple batteries, and then this was it's a grant. It's a research actually, pilot study, and then research where they use a multiple chemistry of batteries, and then they use it for the controlled reserve trading. So this is not something where we deploy in our day-to-day users, but this is a pilot study which was successfully running. Okay. Okay, and okay, now coming back to the electricity market in the world. Okay, Australia, we have the like fast FFR is a fast frequency response, peak frequency response, secondary frequency response, tertiary frequency response. So if you see the time here, okay, forget about this market. If you see the time here, response time is 1 second, 6 seconds, 60 seconds, and then here sometimes like 30 seconds. So here your controller need to be as smart as possible. At the same time, it need to act, and my EMS, so DRMs need to initiate EMS, and then it initiate my BESS to discharge in sometimes less than 2 seconds to 30 seconds. So this is what we are every day in distribution system operator or the load dispatch centers will be handling. So my system should be able to accommodate within this. So if you are a researcher who is working on a controllers, probably consuming battery as a black box, then you make sure your controller is responding, such as your system reaches stability within this period. I mean, you can say, okay, we have IEEE 519, the THD is less than 5%. Of course, without that, you can't do anything. But the response time for the system to be participate in the grid frequency response analysis or grid ancillary services, this should be this small as possible. So here the challenging would be how the communication between my EMS and then the DERMS is taking place and how fast taking place. So that is the reason in the previous slides in Purdue, I told you we will be using the fiber optic cables. As you know very well, our internet's also powered by fiber optic because the speed. So we use fiber optics in most of the site. In case in lack of fiber optics, we use Ethernet for the communication. Okay, fine. We have Ireland, and then this is a European Union. Yep. So as I mentioned, PFR is a contingency up and then down, such as the peak frequency response generally, and then the secondary frequency response also up and down. So these are the flags. If it is up, it will discharge. If it is down, it will absorb or stay idle. The response lasts for 15 minutes, such as once it triggers, okay, within a 5 second or 30 second, it triggers. Its basis discharging. However, the response will be last at least 15 minutes. So until 15 minutes, you know, in inverters, we used to call the LVRT, HVRT, such as low voltage ride through and high voltage ride through. And sometimes it might not be a fault. There might be an impulse where your system will recognize at an impulse, then it will be fine. But if it is recognized as a fault, then corresponding isolators will open. So your system may not be truly stabilized unless you have a capability of LVRT, HVRT. These are the standards it need to undergo, your inverters need to undergo, so that if it is sense some disturbance, it need to be in the position to classify whether it is a fault or it is just a disturbance. So until then, my system will be requesting for the response. Okay, and similarly for mandatory frequency response, MFR, we have a mandatory frequency with primary response sustained for 20 seconds only. Okay, and if you look at mandatory frequency response for secondary response, it will sustain for 30 seconds, such as it's just like our primary response and then secondary response. So obviously it will be a little bit more than the primary. So here, if you see here, the dynamic moderation fast frequency response, this dynamic moderation is nothing but it will be involving in terms of firming and then frequency response at the same, there will be a huge battery. So you will participate in FFR, fast frequency, as well as automatic frequency, as well as manual frequency response. So we call FFR, AFFFR, and then MFFR. So all these three, your system will be ready to dispatch. So this is a dynamic moderation, and it will sustain till half an hour. Okay, so these are a typical ones, and if you come to a regulation, we have up to 1 hour. So why I'm emphasizing on the time is not only the control, your system also need to respond. So here two things comes into picture. As a researcher, you can work on the controller to be as quick or fast or what we call like as fast as possible. As a researcher on active power, you need to size your system to accommodate this. So sizing is a huge challenge. So unless and until we know the load profile, we cannot size. So if I am going to participate in the frequency response or any ancillary services, I also need to size by considering the losses plus my response. I don't know how far my system may require me. So the sizing is a challenging part. So you can develop algorithms to size. Even though we have a commercial tool, even in my office we have a in-house tool. Like day to day, I will work on that every day. And in commercial, we have Homer, and also from Sam from NREL. We have those commercial tools and open source tools. And along with that, you can develop algorithms to do that. So the research area in that is developing algorithm So again, don't go typical algorithms. Why don't you look into much training based algorithms such as machine learning or a neural network or something on I don't say generically I don't say AI, but behind that is again large language model or machine learning is taking place, or even back propagation or forward propagation is only taking place there. So you try to focus on that, so you can develop some algorithms to that. It is active research actually. Okay, so okay, now I want to finalize this with overall futuristic aspect of the application. Very short time period, we have the dynamic reactive response, harmonic mitigation, fault current injection, virtual inertia in terms of grid stability. As the IBR are more, like inverter based reserves are getting more and more in day-to-day life, the rotating elements, the rotating spinning reserve or a synchronous condenser will not be there to feed your inertia. So you need virtual inertia. For that we will use. And short in terms of second, we have the fast frequency response, and then the islanding or a grid forming. So typically everywhere right now is grid following. This is a grid forming, such as if totally blackout, I want to do the black start. So my best with my PCS, the bidirectional converter will act as a grid, and it will form a grid. It's again a challenging research topic goes on among peers, this one. And then in terms of medium, we can bring a black start and then inertia through thermal load flexibility. See, the thermal load is nothing but your generators will be already online during economic dispatch. However, it will take some time to ramp up, right? It will be in terms of minutes. So before that, we can use it for the synthetic inertia. So after certain minutes, your rotating machines can kick in, so that can provide an inertial support. And what else? Like in stationary, we have the grid reinforcement, and then local voltage support to EV charging station, which is my PhD work, and local loss minimization with local reactive power support, such as my inverter can be used as a 100% reactive power source, such as my, the power factor 0.9 to unity. I can go positive, I can go negative. So I can provide you the, the reactive power support. And then capacity firming, as we discussed already, co-located renewable firming. So this is also saying co-located means wherever there is a source, there will be a base, such as solar station with battery, higher floating solar with battery, windmill with battery. That's a co-located. Both are at same place. If it is not co-located, then probably say solar at one side, probably 20 kilometers apart, there will be a base station, something like that. So yeah, as I told, frequency control response, and then the frequency restoration response or the reserve, and here it would be like replacement reserve. So these are the domain where I need to deploy my best as effective as possible. So I will share these slides with the committee. I mean, these are all you can look as controller aspects. However, these are all the future electricity market going to be in the world, not only in Germany, but in the world. Okay, now coming back to finally the renewable revenue, the cost synergy. So why we should do, so whether it is a benefit for us. Okay, this again for the interest of energy economics. Just buy and sell, everybody know. If you probably will be buying a second-hand car, or you will be selling your first-hand car. So what do you look into it? If there is a degradation, okay, then how much I can lose upon? Okay, fine, I can sell it for this amount. Or if you're going to buy something, okay, you will again see degradation. Okay, this is so old, engine model is old, something like that, then you will fix a price, right? Similarly, we will also do that. If it is a new power plant, like probably 2 to 3 years, the energy trading would be very higher. And if it is like a 15-year plant, probably 8-year, 10-year plant, 15-year plant, I cannot retain my energy capacity. So if I'm not able to retain my energy capacity, if there is a degradation, and then my participation in the market also limited. So this is where the energy arbitrage, the revenue synergies, I have to design in a way that I will be getting my payback as soon as possible, probably 2 to 5 years. So whatever the rest of period the system works, it's a profit for me. I need to design in a way that it comes revenue benefit to me in the sense the operators or the independent power producers. And in cost synergy, for example, here, okay, just don't worry about this one. This is a German term. Okay. Here, what I'm trying to look at it is a operating cost is something like how much capex, capital investment, or the operational investment is required to put a battery energy storage system, whether it is benefitable or not. And okay, we came across a decision that it is benefitable. Now, okay, let me put. Now, what is the operating cost to maintain it? Okay, PV panels, 25 years, no problem. Inverters, 5 years, no problem. But BAS, I don't know. So what is that? So will we need to change the BAS in terms of 7 years, or augmentation at 4th year, or every 2 years? So I need to decide. So when I'm doing the financial modeling, I need to key in these parameters by keeping my application in the mind, what purpose I'm going to design and what is the benefit I'm going to get. So these are the two key I need to remember, and then I need to develop my financial model. So in that financial model, I need to consider how much amount is required for this particular operational asset. So this is basically similar to solar. However, when we stepping into the market as a balanced services, then the real money we can see, either money spending or money getting, something like that, what we call like revenue. Yeah. So yeah, so this is what the revenue and cost synergies. So okay, in the last 5 minutes, I would like to say that's all about my day-to-day work in my industry, what I do. It's also quite interactive and effective for us, because every time we will have a new client, every time we will have a new problem, every time we face a new solution. So that's active for me in a day-to-day life. I'll do on daily basis. So if I look further into a research consideration from the presentation, what we'll be looking is, one is IBR resource, as I told earlier, and then the energy economics. If you're not much into developing prototypes, if you're not much into simulation, then probably you are the person to go for energy economics, where you need to know basic economics, and then you play with numbers, and then you can collaborate with some financial experts or fintech guys, finance professor. You can work something on that. Okay, and IBRs in the control, IBR, and then developing algorithm to sizing the best is also challenging research area. It's a general for my electrical engineering background. Okay, and if you are a material background, if you are a chemistry background, probably you can come up with some different material. Unlike lithium ion, you can come, it's already there. You can come up with some more, or you can enhance the existing. And like a solid state battery, where there is no liquid electrolyte will be there, it would be a ceramic layer, and you can use that. And then we have the flow batteries like vanadium, zinc, bromine, and organic solvents. We also have the metal air. Air is nothing but oxygen, iron air, metal air. So iron air basically is nothing but rest. When the iron undergoes oxidation, it will form a rust. So rust, right? Rust, yeah, something. So we need to do that. So anti-rusting, rusting, the cycles. So that's the cycle comes. It's all, these metal air batteries all in the TRL2 proof of concept only. And flow batteries, it's deployed, it's TRL7, and this is TRL6, this is TRL7 and 8. Yeah, lithium ion, TRL8 already. And then if it is an advanced lithium, then you can see cobalt free or a nickel reduced cathodes. We can't go nickel free, but however you can go nickel reduced. And silicon dominant anodes, so changing in anode or electrolyte formulations. If not, probably we'll be having an anode and cathode. So you can reduce the anode in terms of if you remove the anode layer or the current collecting layer, you can reduce the I square R losses. So in turn, you will reduce the heating of battery. So this comes in the material. Okay. And then we have the system integration and control and software. So where we need advanced AMS with AI, of course, and where you can do the predictive analytics to forecast electricity prices. Just for the energy trading, I need to predict, right? So we can forecast and predict, and then we can forecast the load, we can forecast the renewable energy generations, load with high accuracy of optimal bidding and dispatch. This would be a active research. And then is a digital twins. It's another one of my favorite area, my spin-off area, where I contributed to 2 posters and 1 book chapter. And it's a spin-off from my PhD actually. So we can create a digital models of a battery, and you can run a what if analysis, different type of scenarios to see your battery is really doing good or not. It's not only applicable for battery, but also any rotating machines you can use digital twin, or any like probably Prof. Sarthi, IIT Madras, he will be using digital twin for transformers. I know like most people work in high voltage, they are very much preferring using digital twin. And Siemens is pioneer in developing a tool to digital twin. So here, in order to explore this area, you must be competent with a simulation tool, of course, along with a cloud platform, either AWS or Amazon Web Service or Google services, cloud services. You need to be well versed with that, or you need to have at least a prerequisite in that to explore these areas. And then next would be like autonomous grid services, such as it's like writing a PLC programming to control a robotic arm. Just give all the instruction set, it will follow, something like that. There's not of a much research, but it is an active area to explore and test certain controllers. Okay, and then finally it would be a grid forming inverter in terms of control and software. So grid forming is a challenging area. There are a lot of works going on, and some people call VPP, virtual power plant. It's nothing but again batteries. You can term it, even if you are quite a smart, you can term something else, everybody will accept, because there is a lack of terms, but underlying principle is battery. Okay, so if you are into, again, as economics, you can look into revenue stacking, best as a service. Just like cab services, you can put best as services. You install some megawatt, 100 megawatt or 500 megawatt, you use it as a service, you provide it. This ABB is providing this now currently. No other vendor is doing, ABB is doing. Okay, and then the long duration energy storage, where typical BESS will reach up to probably 2 hours, 4 hours systems. And of course, in our office, in our consulting work, we are doing 8 hours also, the pilot study. However, we are looking at 24 hours, like in market is up to 8. We are looking at 8, 12, 16, 20 in terms of 4, And yeah, it's a long duration energy storage. We have in India, there is a separate council for that, long duration energy society, energy storage council. That's a good council in India. Okay, and then finally, if you are into a afterlife research, like circular economy or ESG, then it's a place for you. So you can do recycling techniques. These recycling techniques, you can be a thermal waste to energy, like incineration, burn everything for energy, something like that. And then if you are bio, you can go with the microbial solutions, biodegradations and extraction remediation. And then if you are chemical treatments. So irrespective of your department, you can check on advanced recycling techniques. And second life applications, such as once if the battery is retired, like probably 10 years or 20 years, then we can use it for some other purpose, not only in for the grid services, but some other, unlike say if EV batteries become faded, then I can use that into a stationary, like a home backup system, like our inverter battery. No bad in that, right? That's the second life. So giving a second life to the battery without breaking it, And then you can also do a product stewardship. What we call in abroad is product stewardship. I don't think in India we have or not. I'm not sure. Probably there is. If there is, it would be nice. Such as the product stewardship is something is, okay, today I manufacture a product, you are buying it, you use it. Once it becomes fault or repair, it is life is over, then I will come back and collect it. So only the battery manufacturers are doing that, and not for any other electronic appliances. So that's why we have a huge e-waste. So here the design for recycling means I need to design a system by keeping recycling as goal in my mind. That's what design for recycling. So here you can develop policies. You can research on policy, how other countries doing, how we can bring some policy, or you can bring a hybrid analysis, how you can recycle and what would be the environmental effect of certain recycling techniques. So these things comes into this. Okay. I think next, this one is, it's part and parcel of our control, guys. Failure pragmatics, fire suppression, containment, nothing much different from controlling aspect, because if you are into a controlling, obviously these things comes under controlling aspects. Okay, so I think then let's come to the conclusion. So as everybody knows, I would like to again highlight, it is not a single path, but a multi-pronged effort. So as I remember the first day keynote address, Professor Sarathi mentioning everybody joining together, there's no more electrical, no more mechanical. If I'm not wrong, these are the words he told. Yeah, he mean it. That's what I also mean. So it is a multi-pronged effect. So you just find a suitable researcher, collaborate and do some useful work, then yeah, that's will create a good impact. So however, the challenges remains cheaper, safer, longer lasting, and smarter and fully sustainable. So these are the ultimate goals. Whatever the research we do, we will lead either of this. Okay, so this would be my conclusion of that. I hope I don't bore much of you guys, and yeah, that's all for my presentation today. So if you have any questions, now it's time for you and for your feedback also.
Any queries from the participants? Badrin sir, please unmute if anybody raised hand.
Yeah, I mean, I know it's 7:30 for our Indian audience. I know you will be waiting to do your household work, food, but you can ask few questions.
Participants, anybody is going to ask your doubts, you can ask, unmute yourself and ask, or otherwise
Or put it in the
put
chat.
it in the chat box also. Sir, I have a query, one query.
Yes, please, ma'am.
What are the major challenges in scaling up battery energy storage system for grid level application? And if how the lithium ion batteries compare with the emerging technologies like sodium ion and solid state batteries in terms of efficiency and then with the cost?
Okay, ma'am. As I was giving you initial slides, you want a slide reference, or is it okay for you if I explain
Yes,
you?
yes, it's okay. It's okay.
Okay, fine. Okay, so the thing is that compared to the first of all major challenge, the major challenges is mobility. So I want to transfer, like, okay, even in India we have a manufacturer. However, they bring cell and they assemble here. We don't have direct lithium manufacturers. However, we buy the technology transfer from ISRO. We do that. Last time we did. However, the manufacturers are small and they are only a small scale. So for large scale, like grid scale energy storage, the challenge is mobility, such as I need to transfer all the way from the assembling point to the site. That's a huge challenge for me. The reason is, one is transportation. So there is a possibility, probably you already heard or learned in the articles, where during transportation, the huge battery packs are flamed and the exploded in ships, etc. So the transportation is a big challenge. So to avoid that, we prefer in-house manufacturing. In-house means within India. So if it is an Indian project, it would be suggestible to have a manufacturer in India. Something like a regional manufacturer would be great. And that's a major challenge. Another major challenge would be integrating into the grid. Sometimes the grid infrastructure is also a limited factor. So even though I can have a huge land, I have a money, I cannot inject into the grid. For example, you take an example of our solar in India, we already reached our gigawatt, as our Prime Minister mentioned, we already reached our gigawatt goals. However, how much power you are injecting into the grid is again questionable, because we have a T&D loss, we have still power shutdown in remote places and cities, etc. So probably the grid infrastructure itself kind of a challenging factor to get the best. So if you look at my presentation, I mostly covered in terms of frequency response and ancillary service. The reason is these don't require a grid to be extend or develop. Whatever the existing grid facility is there, it is enough to meet the usage of a BESS into the grid. But however, if I want to do an active power distribution, then I need to have a resilient grid. So, I don't want to bore you with a word called smart grid. It's now outdated, I feel, because everybody says smart grid and they just put smart grid, but really they don't do anything on that. There are a lot of professors in VIT and then in IIT Chennai fight for the term. It's really not smart enough. So of course, it's really still not really smart. But if it is a resilient and if it is really a smart grid, then probably we can deploy BESS as many users scale. And another challenging factor is that conservative people say that, oh, after 10 years or after 20 years, BESS will go. Whatever the money I put, is useless, something like that. No, the payback period is hardly 2 to 5 years. So if the plant is designed for 10 years to 20 years, after 5 years, whatever is there, it's a revenue for you where you can go for the new plant. So it is never going to be a waste at all. So that's understanding most people, like most conservative people or an expert in thermal field, where every day we contract in our office. Even thermal engineers say, hey, come on, man, don't come to us. Something like I say, yeah, you just burn everything for power, burn everything for power. We debate like this because we go renewable. They say like, no, base loads need coal, gas, and thermal. And yeah, it's something like that. It's there, but of course the payback is quite quick. So anybody can dig into that, and then they can put BESS. So there is no bad in that. One thing. These are the major challenges. And if you ask for the comparison of batteries, as of now, efficiency basis, except the flow batteries, all the batteries like lithium ion phosphate, sodium ion is par good, like more than 90%. And however, the flow battery is somewhere around 85. The reason is it involves chemical. It involves the flow of a chemical from one container to another container. Obviously, there will be a thermal loss and there will be losses in the system itself. And if you look for a trade-off between lithium ion or sodium ion, the lithium ion is well matured and sodium ion is upcoming. It's not well matured, it's upcoming, because sodium is abundantly available with us. So it's, we can extract sodium from seawater. So there's no loss in that. So we have abundant sodium. So that's why the reason the sodium ion batteries are getting into more active lines. However, the technology is not so mature. It is under pilot studies actually. Even my study in Saudi also, it's a pilot study. So I want to see how the system behave. So it's under pilots. But there are few countries and few players who deploy sodium ion as a first preference, because based on their consultant suggestions. I mean, yeah, we will. I mean, as me, a consultant, we don't suggest sodium ion as quick as lithium ion. However, we need to see the maturity of the market. So that's the only difference. But whereas if you go for long duration energy storage, like more than 8 hours, 10 hours, 12 hours, flow batteries are right now is best. Only Cell Cube is the company which they are doing the flow batteries. It's a European company. They are doing the flow batteries and they deployed a huge system for flow batteries. We are also studying them to suggest to the new clients, of course. So this is the difference. But nothing but other batteries are all under research. In India, everybody is going for the TRLs. I'll say it's all other batteries are TRL2 and TRL3. Sorry, laboratory proof of concepts. Yeah.
Nowadays, India has set an ambitious target of achieving net zero emissions by
Yeah.
2070.
Okay.
So in this context, battery energy storage systems are often highlighted. So in what role do the battery storage system play in achieving India's net zero emission target, and that is transition to the clean and sustainable energy future?
Okay, here we need to look at two portions or two parts. One is extracting the raw materials for battery. Okay, if you say extracting raw materials for battery, it is not sustainable. It creates emissions. Nobody say no. And if somebody say no, batteries are so clean, no, they don't know, frankly speaking. When we extract the raw material for batteries, it's still having emissions. However, when compared to the other technology, when the active energy is produced, whatever the emission is emitting during that process is nullified. Nullified in the sense, we will have an energy production from any of the renewable source, and we will store it and we will utilize it. So that's why the BESS is highlighted here. However, if the BESS is not highlighted, for example, during night time, I want to run my thermal power plant, such as a steam power plant, either by gas or either by coal or either by waste to like biogas or waste to energy. I need to burn. So these night times or wherever the possible loads where I need to burn coal or I need to burn fuel, there the battery will be utilized. And I cannot say battery is the only way to net zero. No, but battery will make it a little bit faster. It will catalyze. It will act as a catalyst. Yeah.
Okay, sir. Any other questions, participants?
There is a question from Srikant. What is the lifespan of the lithium-ion battery?
Oh, okay. Hello, Shrikant. The lifespan is totally depends on the capacity of the cell. And I'll tell you one thing. In day-to-day work, what we look at the cells from European manufacturers and Chinese manufacturers is that we are looking somewhere around 7,000 to 8,000 cycle. Such as here, what we say cycle is one complete charging and one complete discharging. So I'll give you a simple example. Now your phone is having 40% charge. Now you connected your charger. Now another 20 minutes, your phone will become 100%. Now you will again use the phone for watching video and then sleeping. So this is not one cycle. So it's a cumulative of percentage of charging and discharging will make you one cycle. So in our grid size or grid scale energy storage, we know we will design a system for 1 cycle per day or 1.5 cycle per day, such as in the entire active 12 hour or 24 hour, we'll make sure my batteries will get one complete charge and one complete discharge. Again, here it's not 0 to 100, rather it is 20 to 90% or 90% to 20%. This is the operation we will look at it. So for your question, it would be like 7,000 cycles to 8,000 cycle. And I'm not talking about the small scale lithium-ion batteries which you are using in your laptops or mobile phones. Okay, so 7,000 to 8,000 cycle we are looking at it.
The another question from K. Venkatramanan sir is, how about hydrogen storage batteries which are recently achieved by Japanese? Can it be a game changer?
Hello, Prof. Venkatramanan. So hydrogen storage batteries, what do you mean by that? Do you mean hydrogen fuel cell or something else? If possible, you can unmute and have a conversation. Okay, no worries. So if it is a hydrogen storage battery, you mean if it is a fuel cell, like storing hydrogen and then using as a fuel cell. At the moment right now, as engineers, we look at it, the efficiency of a hydrogen system is 40% less than the existing battery technology. Such as, okay, you can break the water molecule, you can extract hydrogen, and then you can mix with air. You have a fuel, you have an electrolyzer, you have the control unit. Now the electrolyzer or the fuel cell will convert only 50% of hydrogen energy to the energy, electrical energy. So almost 40 to 50% is waste as a heat. So that's a fuel cell market proven technology. Efficiency is only like 49% hardly. So if you prepare electrodes of a fuel cell with a platinum, probably a higher material or very good material. I don't know. I'm not material guy. So probably if you increase the fuel cell efficiency, then of course it can come into the market as a battery, equivalent to battery. But however, hydrogen storage fuel cells is not par with battery. It's at least 40% less than the batteries.
Then there are two questions
Yeah.
from Bhavananthi Rajan. The first one is, blade battery technology is possible to deploy in BESS.
Okay.
Then another one is, the main role for the BESS, in my understanding, is playing frequency response control, where the
Okay.
grid is in an unstable condition.
Okay. Hello, Rajan. So the blade battery is nothing but the structural difference between a normal battery and blade battery is the anode. So because of that, the internal heating, as there is a metal, as the material is copper, if the current is passed to the copper, we know that I square R loss. Basically, it will get heated up. So in a battery, if there is, they are going for anode-free materials. So where the internal heating is avoided, so the thermal efficiency is higher. Excuse me. Anisha, can you make someone to mute?
Yes. Suresh sir.
Sorry.
Sorry,
Okay.
Sorry, Prakash sir.
Yeah, no problem, no worries. So when there is compared to the blade batteries, as of now, the blade batteries, they are deploying in EV, electric vehicles, but not in the grid storage. The reason is the energy density of the blade battery is not up to the level of the storage, like a stationary energy storage. Of course, you can use it, no problem in that. The manufacturer of blade battery is used by the CATL for the EVs, actually. Even for example, in BYD cars in China, they are using the blade battery. But stationary batteries, we don't find any product. I mean, it is like I can't say no. If there is a manufacturer who use their product, no worries. If all the test condition is passed and then if it is within the IEC and IEEE standards, then no problem, we can use it. Okay, that's the answer for your first question. And second one would be the understanding is playing frequency response control where the grid is unstable. Okay, since my presentation is more oriented to frequency response, probably you can drift towards that. However, there is a much more than that. But as I initially mentioned to Dr. Lakshmibai, the grid also plays a vital role. So if the grid infrastructure is not updated, whatever the existing infrastructure is there, I want to deploy best, then ancillary services are the only things I can do. Okay. And second thing, what I can do is firming the power output, such as, okay, you have a solar power plant which is connected to a substation. So you can say, okay, we connected 150 megawatt of solar DC. Okay, so in this 150 megawatt, I say I have a 75 megawatt of battery with 4 times, like say 475, that much megawatt hour of base capacity. Okay, so now here the grid have a capability to have a 150 megawatt. So I'm not going to inject more than 150 megawatt, but rather I'm going to make sure the 150 megawatt is proper, like the power quality profile is maintained. It comes in the power quality research, the power quality. Probably you would have gone through Kundur, Prabhake Kundura, yeah, the same, those concepts. So the maximum limit, grid injection limit is 150 megawatt. However, I have a battery of 75 megawatt with a 305 megawatt hour. I can discharge the battery not only for the frequency, but for the real power itself. Okay, so to meet the intermittent of the solar. So similarly applies for the wind, similarly applies for the hydro. So yeah, I mean, if I don't want to update the grid infrastructure, I can do two things. One is real power and reactive power, and finally frequency regulations. Yeah, so this is my answer.
Thank you, Mr. Prakash. Thank you.
Thank you. Thank you.
Thank you, Dr. Kameswara Satya Prakash, for that highly insightful and thought-provoking session on battery energy storage systems. Your expertise
ma'am.
has certainly broadened our understanding of advanced energy storage technologies. Your presentation on battery storage systems and their role in India's energy transition was truly enlightening. The way you explained the technical aspects while linking them to real world applications was very impressive. Your expertise and dedication to advancing sustainable energy are truly inspiring. We are grateful for your time, effort, and willingness to share knowledge with us today. Once again, thank you.
Thank you so much, Dr. Lakshmi Bai, and thanks for the audience who patiently listened to me. And thank you, Dr. Anisha, for this opportunity.
Thank you, sir.
Yeah, anybody, like any professor who are interested, probably, I mean, since Lakshmi Bai, I think she's from CSE, right? Yeah, you can,
Yes.
you can explore in cybersecurity region of BESS. It's quite competitive right now.
No, sir. Basically, I am electronics only, but
Oh, okay, okay.
working at CSE
Okay,
department.
fine. So anybody like, I mean, I don't know cybersecurity, but I can attach you with proper researchers in Malaysia, no worries. But if you are into power system or power electronics for BESS or a PV, you let me know. I mean, I am in industry right now, but I cannot do research, active research like you, but I can contribute to you for the real-time problems so you can work on. Thank you.
Thank you, sir.